We were up to the final week of Math 1332 in this Summer 2 semester. And on Monday, August 14th, we are going to do the first of 4 review days. Today we're going to be reviewing all the material from week 1. And that's this first review right here, review week 1, and all 4 of these reviews plus the final exam are due on Saturday night, August 19th. So if you do the usual schedule and work review 1 on Monday, review 2 on Tuesday, review 3 on Wednesday, and review 4 on Thursday, that will then give you plenty of time to study and practice before taking the final exam either on Friday or Saturday, your choice. Review week 1, we've got 33 problems here. Some of these were real short answer ones as well. Okay, so identify a pattern that's given in the numbers, then use this pattern to find the next number. More than one pattern might exist, so it's possible there's more than one correct answer. Okay, so I got 5, 25, 125, 625, 3125. Common patterns are adding the same thing over and over again or multiplying the same thing over and over again. If you just saw 5 and 25, you could say that that's either adding 20 or multiplying by 5. But the next number is 125. So then we're adding 100. So it's definitely not adding because whatever it is has to be the same every time. But if I did 5 times 5, 25, if I do another times 5, that is 125. And then 625 and 3125. So it was times 5 for the second one. Is it times 5 for these other two? And remember, in the calculator, this scientific calculator, you can just keep hitting equals and it'll keep doing the last thing you told it to do. So if I hit equals 2 more times, it should give me 625 and 3125. Equals 625 equals 3125. So it is going times 5 over and over and over again. So then I can hit equals 1 more time and it'll do the next one for me. 15,625. Okay, 1, 4, 9, 16, 25, 36. Some of these just take previous experience to maybe recognize what they are. But as usual, you can try things and see if they work or not. If you're thinking adding, you have to add 3 to 1 to equal 4. 1 plus 3 is 4, but 4 plus 5 is 9. And once it's different, it's definitely not adding anything. And 1 times 4 is 4, but 4 times 4 is 16, not 9. So that skipped one of them. Okay, so these are, maybe you recognize it, maybe you don't, but 1 squared is 1, and that's the first one. 2 squared is 4, and that's the second one. 3 squared is 9, there it is. This is 4 squared, this is 5 squared, this is 6 squared. So these are squares. So the next one should be 7 squared. 7 squared, 7 times 7 is 49. Or you can do it in here and do 7 squared. Okay, they often like to do these kind of questions on like IQ tests to see if you can see a pattern in this has geometrical figures. There's a square first, then a triangle, then a circle. And then it apparently repeats because I have the square like the first one, I have the triangle like the second one, and I have a circle like the third one. So it's doing these three things over and over again, and then the square, the dark square without a dot in it, should be the next one. Okay, this is Pascal's triangle. And again, to fill in each one, you get all ones on the outside. And also right here, it always starts and ends with a 1, and those ones just go diagonally down forever on both sides. Any inner answer, you sum the two diagonal numbers right above it. So this 1 plus this 4, that's 5. And then this answer would be the 4 plus the 6, which is 10. And as we talked about back in week 1 about this, if you remember, it's symmetrical the other way. So if it goes 1, 5, 10 this way, it has to go 1, 5, 10 the other way. But you can also add 6 plus 4 and 4 plus 1. Now, one kind of amazing thing about Pascal's triangle is it was kind of just somebody was bored one day and they put a triangular formation of ones. And then on the inner part, you're adding 1 plus 1, that's 2. 1 plus 2 is how you get 3, or 2 plus 1 is how you get 3, and so on. 4, 6, 4. Here's the one we just did, 1, 5, 10, 10, 5, 1. This is all you're doing is simple adding, but there's a whole bunch of patterns in here. I think I mentioned this back in week 1, how this goes 1, 2, 3, 4, 5. And then here you're going up 2, up 3, up 4. But there's also powers hidden in here. 2 to the 0 power is 1. Anything to the 0 power is 1, and there's a 1 right there. 2 to the first power is 2. And if you add 1 plus 1, that's 2. 2 squared is 4. 1 plus 2 plus 1 is 4. So if you wanted to know what 2 to the third was, or 2 to the fourth, or 2 to the fifth, in today's world, we can do this in calculus pretty easily. Like 2 to the fifth, I can type 2 raised to the fifth power, 32. But it turns out it's the sum of that row in Pascal's triangle. And I could add 10 plus 10 is 20, plus 5 is 25, plus 5 is 30, plus 1 is 31, plus 1 is 32. So if you ever wanted a power of 2, you could just add that row of Pascal's triangle to get the sum. Also, the powers of 11 are hiding here too, because 11 to the 0 is 1, and this looks like a 1. 11 to the first is 11, and these two 1s look like an 11. It turns out 11 squared is 121. 11 cubed is 1331. 11 to the third power is 1331. 11 to the fourth power is 14,641, but in Pascal's triangle, that's 1, 4, 6, 4, 1. So it's kind of amazing how all this hidden math is in here. And it wasn't, none of these other things had anything to do with how the triangle was first created. The triangle was just created by adding two numbers together. And now that you guys have learned all 4 weeks of the class, there's some more hidden math in here too. Say I go, they call the row numbers, they start them at 0. So this is row 0, row 1, row 2. The exponent here is the row number. So if I take a row number like row 5, and then I do a combination, and let's do 3, for example. 5 combination 3. If you remember how to do that, it's 5, 4, 3. Stop after 3 numbers. And then in a combination, you divide by 3 down to 1. And 3 cancels 3. 2 can go into 4 twice. 5 times 2 is 10. 5 combination 3 equals 10. But look, if I do row 0, row 1, row 2, row 3, row 4, row 5, and then that's this number, and then this is the column number, but again, you start at 0, column 1, column 2, column 3, right there. every number inside of Pascal's triangle is an answer to a combination, if you ever wanted to look it up that way instead of working it out by hand. So that's kind of amazing that combinations are hiding in there too. And there was a document found, I think in Japan or China, I can't remember which country exactly, but somewhere in Asia, they knew about Pascal's triangle long before Pascal in the 1600s put it in a book. There was an ancient Asian document found over 1,000 years old that had Pascal's triangle in it. And then it got to the Europeans eventually. See, Pascal lived from 1623 to 1662. And he was, at that time, the printing press had just been invented, so people were mass producing books and things. So once he put it in a book and it got spread all over the place for people to see it, that's how his name got attached to it. But it was known well before him. It just called his name because of the printing press. Okay, question 5. We're rounding to the thousandth. So remember, the tenths is the first one. There is no ones. So it's tenths, hundredths, thousandth. Thousandth is the third decimal. So you're either going to leave it like it looks up to that point, 1.343. Those are the first 3 decimals. Whenever you're rounding, you either keep it just like it looks, or you add 1 to this last number. If the next digit is 5 or higher, then you add 1. Otherwise, you don't. So my next digit's a 3. I don't add 1. It's going to stay 1.343. Okay, so this is... Now, this might seem like something we learned later, but actually I'm looking up here. This is still from chapter 1. So this was determine the following estimate without using a calculator. Now, maybe you say, well, I learned how to do it with a calculator later, and maybe that might help you to get the answer as well. But here they're doing this round to the nearest 100. So they're really trying to make this very approximate, where if you do it the exact way that we learned later, you might not get the same answer actually. But you're leasing a car for $303 per month for 3 years. Estimate the total cost of the lease by rounding the monthly payment to the nearest 100. So that's the point, is that 303 is very close to 300. And if you're going to hold this for 3 years and you're doing monthly payments, remember that's 12 months in a year. So you'd actually be doing 36 payments. So you have your $300 a month car payment if you just rounded to 300, and you're doing that for 36 months. One nice thing about multiplying numbers that have zeros in them is you can ignore the zeros and just put them on the end of the answer. So I could just off to the side do 36 times 3. Now it says do this without a calculator. That's why I'm doing this, but you can use a calculator. So you can even do this with a calculator if you want to, but 18, carry the 1, 9 plus 1 is 10, so 10,800. If you have a $300 roughly car payment and you for 36 months pay $300, you'll end up paying almost $11,000. And the problem says round to the nearest 100, not hundredth, but 100. Look for the TH on that. That's a common misconception, but I'm already rounding the 303. So you could have, in theory, done 303 times 36 with a calculator. Now, if you did that, it would get rounded. Maybe they want that. And let's see. Well, they did say without a calculator. Determine the following estimate without using a calculator, then use a calculator to perform it to get the exact answer. Okay. So there's going to be a part B here. So this one should be 10,800 because I just rounded to 300. But if I did it exactly, this is the exact answer. $303 36 times is 10,908. Now, a real car company is going to want the actual dollar amount. They're not going to want a rounded version. It's a $108 difference by rounding that. So the 10,908 minus the 10,800, that's $108. So they're not going to let you keep $100. They're going to want every penny out of you. but the estimate is a little lower than the actual. It's a lower by $108. That would be good for the consumer, but not so good for the car company. And then we had a whole section in Chapter 8 about making car payments, so this was just an estimate of that. Okay, so for problems like this, again, you want to just get to the nearest one. This 0.299 is very close to 0.3. And even if it says do not use a calculator, you can go ahead and use one. There's nothing stopping you from using a calculator, even if you're estimating. So 0.3 times 100, change this 101 to 100 for the estimation purposes, equals, and now divide. This 0.303 is also close to 0.3. So the estimate answer would be 100. And they have a choice for that. This one's multiple choice even. What is the actual answer? That you would definitely need a calculator for. 0.29905 times 101, and then divide by 0.303. The actual answer is 99, round to 2 decimals, 0.68, and then there's a 3 after that. So we don't have to add 1, 99.68. So how reasonable is your estimate compared to the actual answer? This one's a lot closer than the last time. It's only off by 0.32. The estimate's a little higher this time. 100's higher than 99.68. How much higher? 100 minus 99.68. It's off by 0.32. So if this was about money, if you owed somebody $100 and they said, oh, I got $99.68 right now, or you can wait till I get paid again a week from now and I'll give you the whole 100. Somebody might just say, okay, give me the $99.68 just to have the money now. It's only off by 32 cents. Oh, duh. I put the answer again instead of the difference because I was saying out loud that in my head. 0.32. Okay, one person earns $39,000 per year. Another person earns $24.50 per month. How much more does the first person earn in a year than the second person? So how much more? That's a subtraction problem. But the issue is the second person's salary is quoted by the month instead of by the year. So we need to take that second person's $24.50 per month. There's 12 months in a year. So if I multiply by 12, then I'll have a fair comparison where they're both compared to the year. This person makes $29,400 in a year. And the other person made $39,000 in a year. So how does 39,000, how much bigger is that than 29,400? It's almost 10,000 higher. $9,600 more. So suppose you had 2 job offers and one was $39,000 a year and the other one, they just quoted it by the month instead. You could quickly figure this out and see, oh, the first job is definitely a better offer. Each day, a small business owner sells 200 pizza slices at $2 per slice and 85 sandwiches at $4 each. But business expenses come to $90 per day. What is the owner's profit for a 10-day period? So there's a lot going on here. First, each day they sell 200 pizza slices at $2 per slice. 200 pizza slices, $2 per slice. That's $400 they take in each day. Each day. Now we're talking a 10-day period. So if I multiply this by 10, over 10 days, they'll take $4,000 in selling pizza. Then they get $4 for each of these 85 sandwiches. So 85 sandwiches they sell on average every day, and they make $4 per sandwich each day, okay? So 85 times 4. In a day, they'll make $340 selling sandwiches. And therefore, over a 10-day period, that will be $3,400. So in a 10-day period, they're making $7,400 if you add those two together. That's all the money they take in. Now they have their expenses that are $90 per day. 90 per day, and it's 10 days. So over a 10-day period, they're going to have to pay out $900. So expenses are subtracted from money you take in. That determines your profit. So all your income minus your expenses, that's your profit in a business. So they would make a profit of $6,500 every month, or in every 10-day period. What is the owner's profit for a 10-day period? It's $6,500. An automobile purchased for $18,000 is worth $2,600 after 7 years. Assuming the car's value depreciated steadily from year to year, what is it worth at the end of the third year? Okay, so it went from $18,000 when you bought it, and it's now worth only $2,600. $18,000, $2,600 took 7 years to go down that much. So it went down 18,000 minus 2,600. You lost 15,400 in value of a car. Cars go down quite steadily over time, where houses go up actually. 15,400. It went down $15,400 in 7 years. And they said it went down steadily every year, so then you can divide by 7 to get the yearly decrease. If I divide by 7, that means it's going down $2,200 every year. So I could go back to the 18,000 it started off at, and every year it loses 2,200. So at the end of the first year, subtract 2,200, your car is now worth 15,800. Here's where that hitting equals over and over again can help. If I hit equals again, there is the value at the end of the second year, the value at the end of the third year. And if I did that 7 times, it would equal 2,600. But I'm stopping at the end of the third year. The value 3 years after it was purchased is 11,400. Because I just took the 18,000, subtracted the 2,200 on average it was losing each year, and did that 3 times. And if I did it 4 more times, 1, 2, 3, 4 times, there's the 2,600 that it is after 7 years. So that's what's nice about these scientific calculators. You can just keep it in equals if you want to constantly add or subtract something, or multiply or divide even too. Okay, so now we've moved to chapter 2. The nice thing here in the reviews is you can see what chapter and section this came from. This is from 2.1, question number 23. This is when we first learned set notation. So set notation, you put the squiggly. The X just means the variable you're working with, because we don't know what the answer could be. The vertical line means such that. So I want the set of all values such that X has to be a natural number. Natural numbers are 1, 2, 3, 4, 5. It doesn't include any decimals or fractions. So X has to be a natural number, and X has to be less than or equal to 3. Less than or equal to 3, because it could have been just less than 3. If it was just less than 3, the answer would have been B, but less than or equal to 3 is D, and it would be A if they said X is a whole number. Whole numbers include 0, but natural numbers don't include 0, because the most natural thing humans do when they learn math is count things with their fingers. In fact, I don't know if I mentioned this back at that chapter, but the Roman numerals, there is no symbol for the number 0 in the Roman numerals because 0 was a concept that came about 1,000 years ago. People knew nothing that, if you had 3 cows and sold your 3 cows to somebody that you had no cows left, they understood that concept, but to them, putting a symbol for that mathematical unit of nothing didn't mean anything to them. So the Romans didn't even have a symbol for 0. That was a concept that came later. Okay, so now this just says determine if the set is the empty set or not. In other words, is there any way to write any answers down? And this does not say whole numbers or natural numbers. So this includes fractions and decimals. But we need all numbers such that x has to be less than 5 and means at the same time, they both have to be true, x is greater than 8. Are there any numbers that are less than 5 and greater than 8 at the same time? No, because less than 5 is like 4.9 and down. Greater than 8 is 8.1 and up. There's no numbers both of those have in common. So this is the empty set. There would be no way to write any answers down. If it said x is greater than 5 and x is less than 8, if you switched both of these, then there would be some numbers because there'd be like the 5.1, 5.2, all the way to 7.9. Determine whether the given statement is true or false. So here we're going to do these again. Let me start making a list of this again here. This symbol means is an element. In other words, what they have on the left is somewhere inside the set. So I've got a 19 here. 19 is an element of this set. So the only question, true or false, is 19 in here or not? And they don't often show all the numbers because it can be a long list. So this is why we had those pattern problems earlier, like 5, 25, 125. Sometimes you have to recognize a pattern to know what's in a set. 6, 8, 10, ... 24. So this is implying that there's even numbers here. 6, 8, 10, 12, 14, 16, and so on. 19 is an odd number. So it's false that 19 is inside this set. Then you put a line through it. This means you're not an element. Not an element. But when it's true, false, this can get confusing to say it's false that it's not in there. That's like a double negative. So one way I like to do these is I'll do it as if it is an element first. Is 14 an element of 1, 2, 3, ... 9? If it was written in the positive way, is 14 an element of this? That would be false. So then when it's written the correct way, then it's the opposite answer, true. And that way you can avoid sometimes, maybe you could do this one directly and say, yeah, that's true that it's not in there. But it can be confusing sometimes when you get like a double negative that it's false that it's not in there. Okay, this one is false by a technicality. Normally 2 would be an element of the set 2, 5, and 8. If it was written this way, the answer would be true. But what makes it false is they made 2 a set instead of just an element. So this is false because this, as written, is not sitting right there. Although they have another problem later, and I don't know if it's in this review also, but it was in the homework, where another way to make it true is to have sets inside of sets. So if I would put the set 2, the set 5, and the set 8 inside of another set, then it's true because now it's sitting in there. So there are just a couple of exceptions you got to watch out for. If they put a set on the outside of an element question, normally that answer is false automatically. A set is normally not an element of another set unless you have sets inside of sets, which we don't have here. So this would definitely be false no matter what the numbers were or whatever the elements themselves are. Okay, cardinal number means the size of the set. Cardinal number is size. And some sets are infinite. If this was 9, 11, 13, dot, 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 it would just be infinite. But because it stops at 31, it's not infinite. So you could just count this on your fingers and say, okay, 1 is for 9, 9 is 1, then 11, then 13, 15, 17, that's 5, 19, 21, 23, 25, 27, now I'm at 10, 29, and 31. There are 12 numbers in that set. If it's not too large, that's one way to do it. And that's all cardinal number means, is how many numbers are in there. If it doesn't have a dot, 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 then it's a little easier to do, but often they do, so then you got to find some way to count it. Okay, so these are easy to mix up. In fact, I mixed them up when I saw this in chapter 2, because one of them means they're just the same size, and the other one means they're the same size and they have the same elements. And equivalent just means you're the same size. Equal literally means equal, that you're totally equal in every way. And then also remember that order and repeats don't matter in sets. So before you even try to answer this one, I would get rid of the repeats and the out of order stuff on both sets. So the first set has 8, 8, 8, 10, 10, 12, 14, 14. Those repeats don't matter. It's really the same thing as 8, 10, 8, 10, 12, and 14. And even if you left the repeats in there, the cardinal number would be 4. Because in the cardinal number, you don't count repeats either. So this is a size 4 set. If the other set was 1, 2, 3, 4, these would be equivalent. If you had a set 1, 2, 3, 4, that's a size 4. That's equivalent to this one just because their sizes are alike. But it's not equal because the numbers aren't totally alike. 8's different than 1 and 10's different than 2. If there's anything, even if I had like 8, 10, 12, and 13, that would be equivalent but not equal. All it takes is one number to be different to be not equal. But this one's just out of order. 8, 10, 12, 14 backwards. 8, 10, 12, and 14. So these two sets, the two they actually gave us, I made this one up, but the two they actually gave us, they're the same size, so they're definitely equivalent, and they have exactly the same elements one by one in order, so that makes them also equal. And so they're both equivalent and equal. So first they're asking, are they equivalent? Yes, they're equivalent because their sizes are the same. And that's, you put that little n to mean the number of elements. Their sizes are the same. That makes them equivalent regardless of what they actually have inside, as long as you're ignoring repeats and out of order first. Are they equal? Here they are, because they have exactly the same elements. The sets are equal because set A contains the exact same elements as set B. Anytime sets are equal, they have to be equivalent, but if they're equivalent, they don't have to be equal. Okay, then going back to my list, you had these two first, and then you have this is a subset or not. Is a subset or not a subset. And again, by technicality, another set that's equal to the one in question is technically a subset, even though sub normally means smaller or below. But if you're equal to it, then you're still a subset. So every set is a subset of itself. And the empty set is a subset of every set as well. There's also proper subset, which they'll deal with here in a second. So if you put this C shape without the line under it, that's a proper subset. A proper subset, because you would think sub means smaller. So all it does is it takes out the one that's equal to itself. But they have the line under it. So is the empty set a subset or not a subset of itself. Every set is a subset of itself if you have the equal to attached to it. No set is a proper subset of itself, but every set is a subset of itself because of the equal to. And it's easy to remember that because it has the equal to line just like we do with inequalities. Is the empty set a subset, a proper subset, both or neither, compared to this set that's 6 through 100? Well, the empty set is a subset of every other set, including itself, so it's definitely at least a subset. The answer is definitely not neither here. And you would never put just a proper subset. Answer A here is impossible. You should never choose that one. There's no set that's a proper subset that's not also a regular subset, because a proper subset is all the subsets except for the equal one. So A is not the answer ever, and this one's definitely not neither because this is a subset of it. And it could be both. In fact, it is both because it's not equal to it. So as long as you're not equal, as long as you're a subset but not equal to the original, then you're both. Almost every subset you can list is both a proper and a regular subset. Only the equal to one is not both. Here's that one I was thinking of. See how normally this is false when you try to say a set is an element of some other set, unless there's sets inside of sets. And even if there is, you have to have this exact thing in there. So this is the one that's true just because it's literally sitting in there as is. But usually this kind of a question is false. Okay, listing subsets. This will be good for you to understand that problem 2 problems ago. If my original set is AKW, this is a size 3 set. There's a rule that if you do 2 to the n power, that's how many subsets there are. 2 to the third is 8. 2 raised to the third power, 8. So there should be 8 answers here. And if you're talking regular subsets, not the proper ones, but regular subsets, those include the equal one. So any list of full subsets always has the empty set and the original set as 2 of the possible answers. Those 2 are always in there. So that means I need 6 more answers. And the empty set is the size 0. The full set is the size 3 in this case. So what I'm missing are all the size 1s and size 2 sets. So size 1 are easy. You just put each individual thing here. The set A, the set K, and the set W. There's 3 more answers. So now I've got 1, 2, 3, 4, 5 answers. There's 3 to go. There's 3 ways to do them one at a time. So it turns out there's 3 ways to do them 2 at a time. I could do the first 2 letters, AK. Don't put KA as another one. People do that, but repeats and out of order don't matter. So I wouldn't put KA. That's the same thing as AK. So I did AK. I can do KW. That's a different one. And then there's AW. There's all 8. And other than this one right here, all the other 7 are proper subsets because the other 7 are all smaller than the original one. And that's what proper subsets are. So every proper subset is also a subset automatically. There's never a proper subset that's not also a regular subset. That's why you can never be just a proper subset. Every proper subset's also a regular subset. And that's why in those problems where it says, is it a proper subset only? Is it a regular subset only? Is it both or is it neither? Most answers are both, actually. You could certainly be neither if I give you some letters that aren't in the original set, or if I make your size bigger than the original one, then you're going to be neither. And then you could certainly be just a subset If you're the original one, that's the one that's just a subset. So, and in fact, that's the only one. So that's another easy answer. So most answers on those are both. And in fact, when I had that question, I got both for the answer. So most of the time, this is both. Neither is easy because it's just, this is bigger or different than anything over here. And the only time you put this one is if you have the exact same thing as if both of these are exactly the same, you put the second one. And you never put the first one. And hopefully this problem 21 shows you that the list of subsets, 7 of the 8 are proper subsets too. And we should definitely have the empty set in the answer, whether you put a circle with a line through it or just put empty squigglies, that means empty set. So it can't be C or D, they're missing the empty set. It should have the original one if you are asking for subsets. Only if it said proper subsets would you eliminate that one. So choice A are the proper subsets, all 7. Choice B are the regular subsets because it has the same 7 as the proper plus that extra one that's equivalent to the original. That's all a proper subset is about, is you just take the original one away. You would think that would be the case because submarine is under the water, subway is under the ground. Usually sub means smaller or under, so it's kind of weird that the original one counts as a subset. Okay, then we hit intersections and unions, and then the negations too, or the complements. So since we're hitting a new topic here, let me give you my magic word of the day for Monday, August 14th. Send me an email for Monday, August 14th. And in honor of one of the earlier problems we did today, the magic word of the day today is Pascal. So if you don't know how to spell that, go back to that problem. It's listed right in the problem. Pascal is the magic word of the day. And this is problem number 22. So we have a universal set. In this case is 1 through 7. There's a set A, 2, 3, 5, 7. And then there's a set B, 2, 4, 7. They want me to do not A intersection not B. Not A intersection not B. So not A is everything in the universal that A doesn't have. The universal has 7 numbers, A has 4, so this should have 3 answers. A's missing 1. It's got 2 and 3, but it's missing 4. It's got 5, it's missing 6, and then it's got 7. So not A is 1, 4, and 6. Not B, B has 3 numbers, so not B should have 4. B is missing 1, 3, 5, and 6. So then we got to remember, what does this symbol here mean? This means what do they have in common? The upright one means 1 of each without any repeats. So this is what do they have in common? These 2 red sets have 1 in common, and they have 6 in common. So this answer would be 1 and 6, the set 1, 6. If I did this as a union, I would grab 1 of each number. There would be a 1, a 3, a 4, a 5, and a 6. Union answers are usually bigger than intersection answers. This one's just 1 and 6. Okay, this is weird. The universal has just random numbers and they're not even in order, so I'm going to put them in order. That'll make things easier. It's always best to just ignore repeats and put things in order before you try to do anything. So 1, 2, 5, and 10 1, 2, 5, 10. There's a 15, a 14, an 18, and a 20. Okay, so 14, 15, 18, and 20. It definitely helps to have numbers over letters. They're just easier to go in order. Okay, set A. 1, if I put it in order, it'd be 1, 18, and 20. Set B. Actually, they're calling it C, sorry. 2, 5, and 10. 2, 5, and 10. 14 and 15. Whoops, that should be a squiggly. Okay, so I think we want set A union not C. A union not C, yes. So I don't need to do not A since it's not in the question. I'm just going to do not C right here. And C has 1, 2, 3, 4, 5 numbers. The universal has 1, 2, 3, 4, 5, 6, 7, 8. So there should be 3 numbers in not C. It's missing the 1. It's got the 2, it's got the 5, got the 10, got the 14, got the 15, but it's missing 18 and 20. Well, this one's kind of a technicality. If you ever have 2 identical equal sets, these are equal to each other. They're not just equivalent, they're also equal. Then both a union and an intersection have the same answer. Whether I do one of each or whether I do what do they have in common, it's the same answer either way when they both are the same set. But technically, this was one of each number. A union, you grab one of each. And I always take the bigger set, or if they're same size, then I grab one of them and write all those numbers down in the answer. Then I go to the other set, and anything I don't have already also gets included, but I already have all 3 of those. So 1, 18, and 20. This was kind of a bad problem because they should test to see if you know the difference between unions and intersections. When they do this, you're going to get the answer right either way, even if you get it mixed up backwards in your mind. Okay, A union the empty set. Okay, so we need to go through all, maybe they have all 4 of these here, but in case they don't. A union the empty set. Or it might be A intersection the empty set. Or you can have A union the universal set, and you can have A intersection the universal set. These are the 4 possible ones that involve either the empty set or the entire universal set. So the union means one of each thing. So say A was 1, 2, 3, 4. If A was 1, 2, 3, 4, and the empty set's nothing, the union says, give me one of each thing. So I would write all of the 1, 2, 3, 4 down, and because that's the bigger one, and then I would go to the smaller one and grab anything I don't have already. Well, the empty set doesn't have anything to give, so that's everything already. And that's the same as the original, A. So it turns out A union the empty set is the same thing as whatever A is, because the empty set's not going to contribute anything. So A union the empty set is whatever A is. 5, 7, 8, 9. Let's see if they do the intersection one next. Yeah, see, here's A intersection. Well, because these were one of each thing. One of each I needed here. So anytime you're doing one of each, whatever one set has, whether that's the bigger one or not, I always go for the bigger one first, but you don't have to. Whatever one set has to be in the answer no matter what in a union. But if A is 1, 2, 3, 4, and you do an intersection where what does it have in common? What does 1, 2, 3, 4 have in common with nothing? It has nothing in common. So this is just automatically the empty set answer. A intersection the empty set, no matter what set A is, automatically equals the empty set. A can never have anything in common with nothing. Then if you do A union the universal set, A union the universal set, so again, let's say A is 1, 2, 3, 4, but let's say the universal set's 1 through 10, union is one of each. So I would grab the bigger set and put all of that in the answer. When I do unions, I grab the bigger one and I write all of them down. That's definitely in the answer no matter what. Then you go back to the smaller one and say, is there anything here I don't have already? Well, I got 1 through 10 already. So none of these are helping. I already have all of those. So the 1 through 10 answer is the same thing as the universal was. So this is the universal set. So any union with the universal set is always going to be the universal set because that's everything already. So whatever the universal is, that's definitely going to be the answer unioned with any other set. So the point of these 4 problems, if they have the 4th one next, is that these have automatic answers that somebody might know without actually working it out. But the good news is you can just make up an example and work it out. I'm not even doing the example they're giving me. I'm just making it an easier example. But it turns out A union empty set's always A. A intersection the empty set's always the empty set. A union the universal is the universal. And then this one turns out to be A because if A is 1, 2, 3, 4, and the universal is 1 through 10, what do they have in common? They only have 1 through 4 in common. And that's what A was. So out of these 4 possible answers, 2 of them are the original A set. 1 time the empty set's the answer, 1 time the universal set's the answer. So if they have the 4th one next, it should be whatever A is. Yes, see, they do. So whatever A is, 1, 4, 5, 6. Okay, Venn diagrams. So we got these 2 circles that overlap a little bit. And then there's a box around them for that. The box is a universal set. And usually the circles are A and B, but let me not assume. Yeah, A and B. So A has 3 and 5 in this portion of A. That's the stuff that's only A. The 8 and 10 are both A and B. And the 13, 18, and 20 they only like B. And then 23 and 25, they don't like either one of those. I always like to use the example, chocolate ice cream and vanilla ice cream. Say these are customers at an ice cream shop. And every so often they ask somebody, do you like chocolate or vanilla or both or neither? And what if customer 3 said, I only like chocolate? Customer 5 said, I only like chocolate. And maybe the customers 1, 2, and 4, and 6 didn't want to answer for whatever reason. You don't always get people to respond to surveys. Customer 8 and 10, they said, oh, we like both chocolate and vanilla. And then customers 13, 18, and 20, they only like vanilla. 23 and 25, they don't like either one. They like other flavors. We want to do A intersection, not B. A intersection, not B. So this is, what do they have in common? Now this A right here means the entire circle A, even stuff that's in other circles. You would have to literally say only A to just have 3 and 5. So one way to do this is just write down what each one of these things is. A is 3, 5, 8, and 10. When you're doing not B, the best way to do that is just cover up B with your hand. Cover up all of the circle B with your hand. I see these 2 numbers here. And if I cover this up so you can see it, right there you would see the 3 and the 5. You technically wouldn't see any of this, but you'd see the 3 and the 5 and the 23 and 25. So that's what this one is, 3, 5, 23, and 25. And then it could come down to one of each, or what do they have in common? This is what do they have in common. They do have a 3 in common. They have a 5 in common. But that's it. 3 and 5. If it was union instead of intersection, then I would put all 4 of these answers in there for sure. And then I already have these 2, and then I would add these 2 as well. So just changing this to a union problem, the answer would be 3, 5, 8, 10, 23, and 25, which would be a much bigger answer. It would have 6 answers in it instead of 2. Okay, then we switch to where there's 3 sets at the same time, A, B, C, and there'll probably be a Venn diagram too. But here's the one without a Venn diagram first. Problem number 29 we're on out of 33. There's 5 problems left. The universal set is 1 through 7. That helps to keep it small and numerical. We've got sets A, B, and C. A is 1, 2, 3, and 6. I'll just write it without the squigglies to save time. B is 1, 2, 3. C is 1 through 4 plus 6. Okay, we want A union, parenthesis, B intersection C. A union, B intersection C, and the parentheses tell you which one to do first. We have to do B intersection C. Intersection is what do they have in common? Do B and C have anything in common? Yes, they have 1, 2, and 3 in common. So the answer to this parenthesis part is 1, 2, 3. And we already know A is 1, 2, 3, and 6. So now I'm going to use 1, 2, 3, and 6 compared to 1, 2, 3, and we're doing a union, which if that was an intersection also, it could have been an intersection, then I would just want what do they have in common? They would still have 1, 2, 3 in common. But this is one of each. So whenever it's one of each, I always grab the bigger sized one and put all of that in the answer. The answer is definitely going to have 1, 2, 3, and 6, no matter what. Then you go back to the smaller one and grab anything you don't have already. Well, I already have the 1, I already have the 2, I already have the 3. So the second one's not helping me add any more, but I'm definitely going to have the bigger size one in the answer no matter what. 1, 2, 3, and 6. So one of each possible answer ended up in the answer. Some of the numbers repeated, but we never write repeats. Well, we shouldn't write repeats. Okay, same kind of problem, except they switched the union and the intersection, and they put some knots in here. And they changed what the 4 original sets are. So the universal set now is 1 through 10. A, B, C. A is 1, 2, 3, and 7. B is 1, 2, and 9. C is 1, 2, 3, 6, and 8. Okay, so we want to do not A intersection. And then there's a union between B and not C. There is no not B anywhere, so I don't need to worry about that one. I need to do not A and not C. Anytime there's nots involved, I like to just do them right away without even worrying about what the question wants. A's got 1, 2, 3, and 7. That's 4 numbers out of 10. It's missing 6 numbers. It's got 1, 2, 3. It's missing 4, 5, and 6. It's got the 7, but it doesn't have the 8, 9, or 10. C's got 5 numbers, 1, 2, 3, 6, and 8. It's missing 5 of them. So it's got 1, 2, 3, doesn't have 4. It doesn't have 5. It's got 6. Doesn't have 7. It's got 8, but doesn't have 9 or 10. Okay, so take this red one and the regular B in black here. And this is a union, that's one of each. So I'm going to grab the entire bigger answer. 4, 5, 7, 9, and 10 have to be in the answer no matter what. All 5 of those. Now B has a size 3, so I could potentially get 3 more answers. But I already have 9, so I don't need that one. I don't have the 2 or the 1, so let's just tack them on. That's what the parenthesis part equals. The parenthesis part is 1, 2, 4, 5, 7, 9, and 10. Now grab this red one. I'll just rewrite it down here. 4, 5, 6, 8, 9, 10. What does this purple one have in common with this green one? Because this is, what do they have in common? Intersection. They both have a 4. They both have a 5. They both have a 9. And they both have a 10. That's it. 4, 5, 9, and 10. Okay, Venn diagram. List the regions that represent not C. So you got to cover the entire circle C. Cover up this Roman numeral 4, 5, 6, and 7. All 4 of those get covered up. What's left? There's the 1, 2, 3, and the 8. And they want Roman numerals, so capital I, comma, I, comma, I, comma, and then VIII, all capitals. Okay, here's the one where we fill it in what these numbers would be, and they are telling me there's 16 elements in the section 2 that's both, the intersection part. The number of elements in A is 35. This is number 32. The number of elements in A is 35, but that includes the section 1 and the section 2 all the way around circle A. There's 35 elements. The number of elements in B is 38. That's all the way around B, so that's both section 2 and section 3. The number of elements in the universal set, which is my total to work with, is 66. Find the number of elements in regions 1, 3, and 4, because 2 is given to me. In fact, what region 2 is, this little football wedge right here, that's an intersection, really. So the number of elements in A intersection B, that's that middle 16. So they could have put that in the paragraph 2, they just, for whatever reason, didn't. But the way you can do this is, since A has 35 elements, A has 35, including these 16 right here. So if I do 35 minus 16, this 19, that's how many are just here in section 1. There's 19 elements in section 1. That way the 19 plus the 16 will give you the total 35. And then region 3 is done the same way. There are 38 all the way around region B. 38, and there's 16 in the middle. So 38 minus 16 tells you how many are only in B in section 3. There's 22 there. So once we know there's 19, there's 19 here, 16 here, and what did I say, 22 here? Yeah. Well, if you add those 3 together, 22 plus 16 plus 19, I've got 57 out of these 3. But there's 66 total in the whole thing. So these 57 plus something has to give me the 66. So likewise, I can do 66 minus 57 and figure out that there's 9 that are like out in this box right here. And that way, all 4 numbers added together gives you that total of 66. So you've got the 19, that's like the people that only like chocolate ice cream. Then there's 22 people that only like vanilla. There's 16 people that like both, and there's 9 that like neither. And by having all 4 of those, 19 plus 16 plus 22 plus 9, this is what gives me the universal 66 people, or whatever these things are. So 4 must be 9. You're just kind of working backwards to figure out each one of those 3. And that's why if you're building your own Venn diagram, you always need to know that middle part first. How many have both? Which I think is what this problem is. So there's a survey of 81 college students. That's the whole universal. That's like the 66 in the last problem. And it was determined if they got their news, where did they get their news in the world? 39 got their news from websites, 36 from social media, 13 from both. So this is the same problem, just in paragraph form. It's going to be exactly like this. In essence, they told me those same 4 things. So the 39, that's the A part. 39 is the number of elements in A. But that includes the onlys and the boths. There's 36 from social media, that's B. "13 got it from both. That's the intersection one. The middle portion. That's the one you need the most. So 39, 36, and 13. 39, 36, 13. And then the 81, that's the universal. They just mentioned it first this time instead of last, but that's the total number of people surveyed. So you do this exactly the same way. You make your own Venn diagram. And the key is to put the both in the middle. You always need that middle part first. The 32 is nice because they did it for you, but here you just have to know that. And then it's just 3 subtractions to get the other 3 parts. So 39 minus this 13 will tell you how many are just in A. 39 minus 13. 26 people only get their news from websites. And then if you do 36 minus 13, 23 people only get theirs from social media, and 13 get it from both. So 26 plus the 13 in the middle plus the 23, there's 62 of the people in the whole survey get their news one way or the other or both. But there's still some people that aren't in there yet. Out of the 81 people, I've only got 62 accounted for. So 81 minus 62, there's 19 that get their news some other way. Maybe they watch the TV and get it, or maybe they read a newspaper, or maybe they hear it from a friend or something. It's not on social media or something. So that way, if you add all the numbers together, 26 plus 13 plus 23 plus 19, this is supposed to equal 81. Yep. Okay, so now I just got to fill all these in. How many people get it from websites only? That's the 26. How many get it from only social media? That's the 23 over here. And then the or, how many got their news from websites or social media? The middle portion is and. This is and, not or. The or means all 3 of these added together. So that was not so. I actually figured that out, but that's not something you normally figure out. I guess you did have to know that. That was 62. The reason they're asking for that one is that's how you get to the last answer. It's not a number in the chart itself, but it's needed to get that universal number. And then how many are neither? That's the 19. The 81 minus this third answer is how you get the fourth answer. You just have to be careful in that third one because it said or, not and. Somebody might think they're talking about the middle portion and try to put a 13 there. But luckily I caught that before I put in the wrong answer. Okay, so there's 100 on all 33 of these problems, and this was not too long of a video, only just an hour and 10 minutes. So that didn't take too much time. That was shorter than an average set of homework. And we've now got one of the 4 reviews finished. And this was for Monday, August 14th. Monday, August 14th. And I got a green check everywhere there. So on Tuesday, August 15th, we're going to do the second review. Wednesday, we'll do the third review. Thursday's the fourth review. And then the final exam appears Friday morning. You can do it anytime Friday or Saturday one time. So see you tomorrow for review number 2.